This is Group 2A's Lab Report 2 on resistive forces.
The purpose of this experiment was to look at the relationship between the velocity of an object and the drag and viscous forces on said object. We did this by examining the velocity of a metal ball bearing dropped in 3 different fluids, and then calculating the drag, viscous forces, and Reynolds coefficient. Our experimental design was relatively simple. For our materials, we used ball bearing, a magnet, graduated cylinder, and 50 milliliters of dish soap, water, or corn syrup. First, what we did was we dropped the ball bearing via the magnet through 50 milliliters of one of the liquids. We changed the liquids to understand how the different viscosities of fluid affect the drag force and movement of objects through said fluids. There were some limitations to this experiment. 50 milliliters was not enough liquid for the ball bearing to reach terminal velocity in either the dish soap or the water. This means that our calculations due to drag, viscous, and Reynolds coefficient will be altered. The release of the ball bearing also will create some initial force from the magnet, and that cannot be accounted for within the graphs. We also cannot accurately measure the exact friction coefficients for corn syrup and dish soap.
This slide shows on the left the system schema for our experiment, and in it we have the fluid, the graduated cylinder, the earth, and the metal ball bearing. And on the right side are the energy pie charts for water, corn syrup, and dish soap. So it starts out as all potential energy, and then as it falls through the fluid, it gets converted to internal energy and kinetic energy. This is an example of our experimental setup with dish soap. There are a few physics concepts needed to understand everything we did in this experiment. First, terminal velocity is when an object is falling toward the Earth due to gravitational interaction, but the object's net acceleration is 0 due to resistive forces. Drag forces are resistive forces due to a solid object moving through fluid. Viscous forces are resistive forces between a solid object and a fluid that opposes the flow of fluid past the object. And finally, Reynolds number is the ratio between drag and viscous forces on the object, and this tells you which force dominates.
As you can see, only the corn syrup and dish soap reach terminal velocities. We can tell this because the position graphs are largely linear, meaning as we look at the velocity graphs, they seem to hover over a constant velocity. In addition to this, they also hover around an acceleration of 0, which makes sense as there's no acceleration at terminal velocity. Water, on the other hand, does not seem to show this trend. To begin analyzing our data, we first calculated the terminal velocity for both corn syrup and dish soap. In order to do this, we found the slope of the most linear portion of the position graph, change in distance over change in time. We use this variable v to plug into the equations for resistive forces of drag and viscosity for corn syrup and dish soap. For the drag and viscosity coefficients, we use the internet. Lastly, we calculated the Reynolds number, which is just a ratio of drag force over viscosity. Further analysis shows water never reaches the terminal velocity. This means the drag force and viscosity never equal the force of gravity in our experiment. If the ball bearing was dropped in air over the same distance, the final velocity would be larger, assuming there are no resistive forces in the air. The drag and viscous forces are still acting upon the water, just not to its maximum. Below, we compared the calculation of final velocity in air versus the tracker results of velocity flowing through water. As we can see, the final velocity of air is much greater. In conclusion, viscosity is the dominant resistive force on the ball bearing in both dish soap and corn syrup. We can tell this because the Reynolds number is much below 1, meaning the denominator, or viscosity force, is much greater than the drag force on the numerator. A ball bearing in water does not reach its terminal velocity over the distance of 0.165 meters. For future experiments, we would like to take the mass of the ball bearing in order to find the force of gravity being placed upon it. In addition to this, we would like to increase the distance the ball travels through water to see if it can reach its terminal velocity.